Okay, well, thanks very much, David, for that intro, and welcome to today's GeoTalk today, everyone. So, as David said, I'm going to be talking about lakes, rivers, and maybe a little bit about waterfalls in Antarctica, and specifically how we model those or how we create computer simulations of what's going on there, because obviously Antarctica is pretty far away, it's quite hard to get to. So a lot of our understanding of our polar regions has to come from using the information that we do have to then do kind of computer simulations to work out more about what is actually happening down there. So before that, just a little bit about me, so you know who's talking to you today. I did my PhD at the University of Reading in the UK. I then moved to University College London, where I worked on a project funded by the European Space Agency looking at Arctic sea ice, so the opposite polar region to the one I'll be talking about today. Before I then moved over to the US for a couple of years, working at Georgia Tech over in Atlanta. And then mid-pandemic, I say mid-pandemic, it's not over yet, but kind of mid-heavy lockdown, I moved back to the UK to start a lectureship at Cardiff University just over a year ago now. So to kind of motivate why we care about lakes on Antarctica, and this is a satellite image of what was the Larsen B ice shelf in Antarctica. So satellite image, we're looking down from space, the white areas you can see are ice, dark areas are ocean. And the reason I say this is what was the Larsen B ice shelf is because quite quickly after this situation, we can see here, so ice shelves sitting next to the ocean, we had this sudden and dramatic collapse right across the ice shelf. A lot of scientists talking about this event said the area of ice lost was about the size of Rhode Island in less than a month. But as I'm now back in the UK, I'm going to change that into a measurement you might actually understand, because I certainly did not know how big Rhode Island was before I had to drive across it while I was over in the US. But this is about 2 Greater London's worth of ice. But regardless of if you know how big Greater London is, it's very clear that that's a lot of ice lost very suddenly, basically in less than a month. So a very, very dramatic event that happened there in Antarctica in 2002. And the reason that we care about these sudden kind of losses of ice shelves is because that is going to ultimately lead to a contribution to sea level rise. And now the ice shelves themselves, they're kind of the floating parts of Antarctica that surround this frozen continent. So they don't directly contribute to sea level rise when they collapse because they're already floating on the ocean. It's a bit like if you have a nice gin and tonic on your Wednesday evening and you've got ice cubes in that. When they melt, the water level in your glass isn't going to change. But the thing about Antarctica is because it's surrounded by these ice shelves, they're holding all the ice that's on the land in Antarctica in the middle of the continent back. And if you take them away, like happened with Larsen B, then all that ice is going to speed up and flow off the edge of the continent and end up in the ocean. And that was observed to happen after Larsen B collapsed. All the glaciers that used to feed onto that ice shelf and were kind of held back by that ice shelf accelerated, and we got some sea level rise as a result of that. And we can see here that Antarctica is contributing to sea level at the moment, though not as much as Greenland. Even though Greenland is much smaller, that's the one that's kind of melting faster at the moment. But between them, that contribution to sea level is accelerating. And we can see we're only getting a couple of millimeters per decade back in the 90s. Now the combined contribution of both of those continents is around 30 millimeters per decade and going up. And the thing we want to know is essentially how much is that going to go up from Antarctica? Because Greenland is big, there's a lot of ice in there, but it's nothing compared to Antarctica. So even though Antarctica is kind of contributing more slowly at the moment, if that arrow keeps on going up, we're going to see a real lot of sea level rise. And so what my work is trying to find out essentially is how are those ice shelves that are currently protecting Antarctica from contributing too much to sea level rise, how they're going to change in the future. Are we going to see more losses like we did with Larsen B? And is that going to lead to the kind of sea level rise contribution going right up? But I'm actually a mathematician by background, so I showed you a nice satellite image of Larsen B, but when I think about ice shelves, I think about them more like this. So as I said, ice shelves are floating on the oceans. You have a big, solid lot of ice and can be kind of hundreds of meters thick. And on top of that, you have a layer of snow, or what we refer to as Fern, which essentially just means old snow. It's snow that's been there for more than a year. So ice shelves have light fluffy snow at the top, and then they get denser as you go down into more and more dense ice. And one thing I will highlight here is, I can turn on a laser pointer. There we go. So this pore closure depth here it's where the snow hasn't kind of compacted quite enough that it's ice, but any water that may get into that snow, which is going to become important later, can't get through. It's essentially impermeable to any water. So that's basically the depth of the ice shelf that I care about, because anything below that I don't really think about in terms of this work specifically, although ocean melting of ice shelves, I should say, is also very important, and there are lots of really smart people working on that problem too. Ice shelves kind of have a two-pronged attack from climate change, because they're getting warmed on their surface, and the ocean warming is kind of melting them from underneath as well. So they're not having a lot of fun as things are changing quite so dramatically as we're seeing at the moment. And so yeah, this is the area of the ice shelf that I care about. And the reason that I care about that in terms of, so this is going back to that same satellite image of Larsen B, but we've now got a little zoomed in area, and hopefully you can see these kind of dark features on the zoomed in part of the satellite image. And these were lakes that were present on the Larsen B ice shelf. And what was noted just before Larsen B collapsed is that these lakes started to drain. So first one would drain, then those around it, and then those around that, in a chain reaction that we think was key to the sudden collapse of the ice shelf. So that's why I care about the top of ice shelves. So I want to know where they're melting and what that water's going to do to the ice shelf. Are we going to see these kind of chain reaction lake drainage events that could cause future ice shelf collapse elsewhere? Okay, so to look at how these lakes could be forming on other ice shelves, there are three possible things that could be going on here. So our first example, we've got the light fluffy snow here, and the dense ice below that, and then the pore closure depth here is where water can get up to. So there are three possible ways we could get these lakes forming on ice shelves. The most simple one is we get some melting at the surface, water percolates down through the snow, it'll reach the pore closure depth, and then we'll kind of saturate the snow from the pore closure depth upwards until there's enough melting that that water's got nowhere to go and it forms a lake. This may be happening in some areas of Antarctica, but there are also some areas of Antarctica where this kind of distance between the snow and the pore closure depth is about 30 meters. So that's a lot of water needed to form a lake. But ice shelves aren't completely flat. So another possibility is that we get some melting in some areas. Maybe it will reach down to the pore closure depth, might saturate a bit of the snow, but not all the way up to the top. But if we look at kind of lows in the ice shelf, so the surface is going to have high areas and low areas, surface melting from the high areas will end up in the low areas. And that may mean that enough water kind of gets transported into certain areas that we get lakes where these lows exist. Finally, another possibility is that because Antarctica, as you probably all know, is quite cold, actually when that melting at the surface occurs, as soon as it gets down a little way into the snow, that snow is going to be below the melting point of water. So you're going to get some of that water is actually going to refreeze in the snow before it even gets down as far as the pore closure depth. And if this happens, what we get is something called an ice lens, which is an impermeable layer of ice, so refrozen water just forms within the snow. And this means that any further melting, instead of going down to the pore closure depth, is going to sit on top of this ice lens. And actually we need much less water to saturate now the snowpack from the ice lens upwards to form a lake. So in terms of lakes forming, this is kind of bad news for the ice shelf, because they're going to form much more quickly if we get these ice lenses forming than if the whole snowpack was having to be saturated. Now, one of the kind of case studies I've done looking at this is the Larsen C ice shelf. This is Larsen B's next door neighbour. So if you think of kind of a map of Antarctica, it's kind of like mostly round and has a bit that's sticking out that kind of goes up towards Chile. That sticking out bit is called the Antarctic Peninsula. That's where Larsen B was located. And Larsen C is kind of the next ice shelf down from that. So it's currently Antarctica's most northernmost ice shelf. And the reason that we're interested in it is if I just zoom into the top of this satellite image, hopefully you can see these kind of black smudgy features. on the satellite image. These are lakes that are forming on the Larsen C ice shelf. Now, it doesn't look like Larsen B at the moment. It's currently got a lot more snow, and the lakes are really confined to just this kind of small part of the ice shelf. But we want to know how this ice shelf is going to evolve in the future. Are we actually going to see more lakes forming across the whole ice shelf? Could it be in danger of sudden collapse like Larsen B? So to understand that, we're trying to work out how these lakes are forming. So to do that, I ran some computer simulations, and I won't go into the details of those now because that involves too much maths for 5 p.m. on a Wednesday. But we can see that my initial simulations of trying to work out which of those 3 situations were occurring, and just looking at water kind of percolating down into the ice shelf, gave us some weird features that we can see on these line graphs here. So here, on the y-axis of the graph is the depth into the ice shelf. So 0 is the top of the ice shelf, and then negative numbers are looking down into the ice, and then density is increasing across the x-axis. And we can see here that after kind of running our simulations of how the snow might change in Antarctica, we've got this kind of big chunk of high density ice within the ice shelf. And if we look at the water content of the ice shelf there as well, we can see that not only have we got high density areas, we've got water that's starting to build up on top of that, kind of in just 10 meters below the surface of the ice shelf. So this is quite interesting because it shows that we were getting water kind of percolating down into the snow, refreezing. There's some ice in there, there's some water in there, but it's not forming a lake. The top 10 meters of the ice shelf were kind of fluffy snow, not really changing. And that continued to stay that way even if we carried on our simulations beyond the first year. So something was going wrong, because when we're trying to simulate lakes and we're not getting lakes, that's not ideal. So I had to ask myself what are missing from the simulations. And first of all, a problem that is very, very common when you work in the polar regions is that actually the data we had was not located quite in the area that we wanted. Antarctica is very difficult to get to, and there's not a lot of measurements been taken of a lot of areas, so sometimes we have to work with less than ideal data. And in this situation, the kind of weather station data that I'd been using to run my simulations to tell me what temperatures were happening on the surface of the ice shelf, they were actually further down the Larsen C ice shelf than where those lakes were. So actually, the fact that we weren't getting lakes in our simulations was quite a good thing, because there weren't any lakes where the weather station was. But the point of this research was to understand how the lakes are forming. So we had to think about what processes maybe were happening up here in the ice shelf that weren't happening kind of down here where the weather station was located. And one very key thing that is happening on the Antarctic Peninsula is the occurrence of these Fern winds. So if I just pop back to the satellite image, you can see here these kind of features along the edge of that. They are mountains. And what happens is that when kind of air reaches one side of a mountain, moist air is forced up and over the mountain, so it's got nowhere else it can go. But that kind of upward movement of it causes a lot of the water to condense out and causes the air to warm up. So when the air gets to the other side of the mountain, you get this warm, dry air that rushes down the other side of the mountain. And we can see that if air is coming from this direction, going over these mountains and down here, we've got lots of warm, dry air in the mountains that's going to then heat up the ice shelf. And that's very key for the formation of those lakes. So we had to add in this kind of Fern wind effect to our simulations to kind of account for this. And they gave us kind of some results, but still we weren't quite getting the lakes we wanted. And that problem was because I was only thinking about things in one dimension. So I was just thinking about kind of melting at the surface and then kind of the vertical percolation of the water down into the ice shelf. Because, to be honest, that was kind of the easiest way to do the maths and the easiest way to code it up. But unfortunately, Antarctica is not in one dimension. And as I kind of hinted at when I showed you those 3 possible scenarios, movement of water across the surface of the ice shelf is actually very important too. So if I can just get this video to run, we can see this is the Nansen ice shelf in Antarctica. So not only do we see a fast flowing river here, there's actually a waterfall going on. So it's even more complicated than those lakes we saw at Larsen B. So at that point, I realized I was going to have to actually kind of bite the bullet and turn this into a more complicated model that also accounted for this kind of transport of water across the surface as well, because it's just occurring in so many places on Antarctica. And we can see here from this image, there's the waterfall that I just showed you. There are ridiculously big lakes on the surface of Amory ice shelf that are like 80 kilometers on. There are lakes below the surface. There we go, so those are the Larsen C ones, those lakes that are forming because of the Fern winds, but it's just happening all over the continent. So in order to do that, I created a model of surface melt on Antarctica called Monarchs. It was the model of Antarctic ice shelf surface hydrology and stability, which is a pretty terrible acronym, but still took a long time to come up with because they weren't the easiest bunch of words to put together and make into a fun name. But what Monarchs does is it takes all of those kind of one-dimensional vertical things that I was thinking about, so the melting at the surface and that water going down into the ice shelf, and turns it into a grid. So we think about all those processes, but we can also move water across the surface of the grid. And this allows us to think about things like the formation of lakes, the formation of rivers, and how water kind of erodes channels on the surface. And also more complicated things like how the ice shelf might flex when lots of water ends up in one place. And this then allows us to think about kind of the surface melt distribution over any ice shelf on Antarctica. So yeah, I have time to talk about this part. So the thing that was kind of particularly new about this was thinking about how water goes across the surface of the ice shelf. And so this is just a little proof of concept of how that works. So we can see here, first of all, in the red diagram, an initial kind of surface height we gave the simulation. So here, red is high, white is low. We can see this in our kind of fake ice shelf scenario. There's a very big kind of low area in the middle of this area, but also kind of two slightly smaller lows there as well. And we just give it an initial distribution of random water. So we chuck some water kind of across the surface of the ice shelf just to test it out. And what we expect would happen is that some water would go into these kind of small lakes, but then eventually they would fill up and all of the water would mostly end up in this kind of big low in the middle of the ice shelf. And that is thankfully what happened in the simulations. So the most interesting one here to look at is the blue one, because blue is kind of where there's more water. So you can see that not only has that big lake filled up in the middle, but these two smaller lakes have filled up, and you can actually see some kind of leftover water that's trickling down from those small lakes into the big one as well. So to do that with a real glacier, instead of just making up kind of nice circles, we kind of know what would happen with them. This is the Pine Island Glacier. It's in West Antarctica. And you can see here we gave it a high distribution of the snow surface from observations, and then water moves around to kind of form these sort of long lake or river features that have been observed on the Pine Island Glacier. Again, just because I quite like making these kind of animations of this is the Roy Bedouin ice shelf. So a similar situation, if we take the existing kind of surface heights or topography of the ice shelf, we can look at where water ends up on that ice shelf surface. So doing that, I'll just skip over these in the interest of time. But what then happened in terms of looking at Larsen C, when we could look at things in kind of more of a 3D fashion, is that we saw the formation of these ice lenses. So looking here at how the density profile has now changed. So once again, 0 is the top of the ice shelf, negative numbers are looking down, increasing density across the x-axis. And if we zoom into these kind of spiky features at the bottom of this density profile, we can see that these ice lenses that are forming on the Larsen C ice shelf according to our simulation. So if you remember when I showed you those 3 possible ways lakes could form, the final one where water was refreezing within the snow and forming these impermeable lenses of ice, that is what our model simulations were predicting happened on Larsen C. And quite nicely, around the time that I was doing these simulations, some colleagues from Swansea University were conducting some fieldwork on the Larsen C ice shelf. And while they were there, they dug some snow pits in areas where they thought there'd been a lot of melting. So here, this is about 2 metre snow pit. So they dug an identical one directly behind it, kind of shone a light between them. And from that, you can see here these kind of layers of solid ice within the snow. So actually really nicely, the field observations were backing up what happened in my model simulation, even though this was happening kind of thousands of miles away in the UK. One kind of key thing that we found actually was that once these lakes started to form, you got more lakes much more easily in subsequent years, because once a lake forms on the surface of an ice shelf, it's going to refreeze again as Antarctica goes into winter. We don't think, probably at the moment, we're getting lakes that can sit there all year round because it just gets too cold. So in the same way that lakes in the UK, you can kind of get a layer of ice forming over them in the winter. This happens in Antarctica, but much more extreme in that they probably completely freeze over the whole lake. But what this figure here is showing, so here, yellow is the higher density and blue is less dense. So we can see we start out with a profile within the snow going from less dense down to more dense. We get around the Antarctic summertime when we get lots of melting, so that would be the opposite of our winter time. We get increases in density here. As all this kind of water piles into the snow, it refreezes, it saturates all the snow, you get a lake. And when all that is frozen into ice, what you're left with is a big chunk of ice sitting on top of the ice shelf. And the next year round, all that has to happen is any new snow has to melt, and you've got a lake already. You don't have to form these ice lenses to get a lake. So it's kind of, once they happen, you get them more and more easily in subsequent years. And we thought about these in terms of kind of future climates as well, because even though I said at the moment we think the lakes do currently freeze over in the Antarctic winter, it's possible that might not happen in the future. And the kind of key takeaway of this result was we looked at increases in temperature. So here they're in Kelvin, but we can still think about these in terms of the equivalent change in degrees centigrade. So just changing kind of half a degree, one and a half degrees in the future, and also increasing the snowfall on the ice shelves, because we think that both those things are going to happen in our future climates, resulted in deeper lakes that aren't actually going to refreeze over during the winter. So we suspect that in the future on Larsen C, we'll be able to see lakes that will potentially form all year round if we do see these kind of changes in temperature and snowfall or precipitation on the ice shelf surface. Just to show you kind of one more animation of what this kind of model can do, in January of 2020, well, I should say just before January of 2020, some of my colleagues went to the Georgian Sixth ice shelf, also on the Antarctic Peninsula, and left lots of instruments there to hopefully get lots of data to help to run my model simulations with. And then in January 2020, the satellite images showed us this here. And this isn't like a false colour satellite image, this is just what the satellite saw. It really was that blue on the ice shelf surface. Georgian Sixth was absolutely covered in lakes. Which my first reaction to that was, oh, okay, well, all those instruments are now just floating in a lake, and that's probably not going to get me a whole lot of data. But my second response was like, oh, this is a really nice way to actually test the model. We can see if we can reproduce these lakes. You can see here that the model did actually do that pretty well in a couple of ways. So first of all, you can sort of see this horseshoe-shaped feature in the red circle. It picked that up really well. And up here, it's kind of got a bit more of a river than a lake. So this was kind of an interesting way to think about what the model's still not doing quite right, that it didn't get that lake. So also a good case study there to test out how to improve the model. So I will finish up there, so we've got time for questions. But if you want to read more about this, because I know this was kind of a whistle-stop tour of kind of ice shelves and water on ice shelves, I recently wrote an article for Physics Today, which is available for free on the internet, around Antarctica, and with some kind of helpful images to help explain some of these processes a bit better and let you kind of take it at your own pace. So please do check that out if you're interested in it, and share that with friends and family who might want to know more about what's going on Antarctica. And with that, I'll say thank you very much, and I'm happy to take any questions.
Thanks a lot, Sammy, for that quite interesting talk. really interesting to see what you can do with modeling. And I mean, the last images you show are very convincing. You can reproduce these features. It's pretty cool. So for the people interested in asking questions, could I ask that you use the chat, please, to write them down? Or if you want, you can also unmute yourself. But yeah, remember, this is recorded. Is there any question? Well, there might be a question coming from the attendees. In the meantime, I have just a general question. What sort of computer do you use for your modeling? Do you need like really powerful computers, or you can do this with a kind of usual, I don't know, desktop computer you can have in your office?
It depends on how complicated the model is. So one of the reasons that I first focused on those kind of just one-dimensional processes, looking at kind of where water went vertically in the ice shelf, is you can simulate that on a computer just like the one I'm using to talk to you now, or on like a laptop. But if you do want to then make the model into 3D and look at how water is going across the ice shelf surface, that does need kind of higher computing powers. So using kind of the Welsh supercomputer here that we have access to at Cardiff, or previously I was using different supercomputers to run this work. So it is quite computationally expensive, or like it takes a lot of computing power essentially to run those simulations.
Yeah, fair enough. And then, so when you run one of these 3D models, how long does it take? I mean, I guess it depends on the size that you're modeling, but I mean, practically, how long would you like these models to run for?
Yeah, well, that's kind of a question that I'm still trying to figure out, because it depends on how big an area you're trying to look at, and how much detail you want to look at that area in, because you can look at a whole ice shelf and just say each kind of grid square on the ice shelf with several kilometers, but then you might not pick up those lakes that are forming. So it depends on how big your grid is, but then also how long you want to run it for as well. Because if you just want to know where the water's going to go in a single year, it doesn't take too long to run, less than a day certainly. But if you want to look at kind of like long-term climate changes, then yeah, that's a bit more of a chunk of computing time that you need.
Right, fair enough. I don't know if you can see any question. I can't see a question on my side, I think, coming in the chat. It was just some talks in the very beginning with one of the attendees, but that's all. Yeah, so I've got many questions. I could go on for quite a bit of time. But yeah, the other question I had is then for what's the maximum duration of your models? How long, in terms of time, trying to reproduce what's happening from one year to another, have you gone for? Is it 10 years? Is it 50 years? Is it several centuries?
At the moment, I've only really looked into like decades to kind of a century, but I mean, there's no reason you couldn't look further ahead. There's just obviously a lot more uncertainty as to what conditions Antarctica will be experiencing 100 years in the future. So that's kind of, yeah, it's interesting, but there's a lot more guesswork involved at that point, but there's no reason you can't do that.
Yeah, fair enough. And I guess that could be my kind of concluding question. This still a technical question, but I'm just interested in the potential of this kind of modeling. When you imagine some ice shelf, it looks like it's not moving, but obviously it's a glacier, so it's going to move. Yeah. And I was wondering whether the motion of the glacier itself could influence the formation of the lakes. In the sense, well, obviously if the ice is moving around, they might have some differences in the pores in this kind of snowy layer at the top. Is this something that should be considered, or your models are apparently not using the motion of the ice or not integrating the motion of the ice, and you're already able to reproduce some of the key features that we can observe remotely? But I was wondering whether you think it's something that could have some potential, just adding some motion within the ice.
Yeah, and it's actually something we're considering doing in the future. Oh, right. So taking kind of existing ice sheet and ice shelf models that already do have that kind of flow of the ice in them, and then linking them up with my model to see what would happen. Yeah, but you're right, at the moment I don't really think about that, because a lot of the kind of surface features we see on ice shelves, those kind of like high and low areas that determine where the lakes are going to form, they kind of flow down the ice shelf with the ice. And in a lot of cases, they don't really change as they go down the ice shelf. So in terms of what I'm looking at, it doesn't matter so much, but it could be something that becomes more important in the future for sure. So for example, when I spoke about the Larsen C ice shelf, if you're up near the mountains, then you might get a lake, but then once that's kind of flowed all the way down the ice shelf, and like that takes years and years and years, maybe it will be experiencing different conditions and it might not have a lake. So certainly thinking in kind of those longer term simulations, yeah, we do need to consider that, which is the next step of the work. Great.
Yeah, thanks a lot, Sammy. Really interesting stuff. Yeah, so I think that's all for today. Thanks everyone for attending, and spread the word about the GeoTalks. They're gonna happen again in forthcoming weeks. We have another talk on corals and climate change. It's gonna be mid-May, so it's all explained on our program on our internet website. If you want to catch up on some of the talks that you've missed in the past, don't hesitate to look at our YouTube channel. And I'm looking forward to seeing you again in the near future. Thanks, everyone.